Welcome to our Chapter 8 review for Precalculus. This chapter covers sequences and series, as well as permutations and combinations and probability. So the very first two problems, though, here are from conic sections from our last test. So we will have to remember back to what we did before this. On number 1, we are asked to write the equation of a hyperbola. And then on question 2, we need to write the equation of an ellipse. These are going to be very similar. They both have fractions that equal 1. The difference between a hyperbola and an ellipse as far as the equations go is that a hyperbola has a minus sign in between and an ellipse always has a plus sign in between. For a hyperbola, it matters because of that minus sign whether x or y is going to go first. And so since on this particular hyperbola, our graph is on the top and the bottom, right there, that means that y is going to go first. And so we're going to have y inside of parentheses squared and then x inside of parentheses squared. On the other hand, on ellipses, we just always put x first and y second because it's addition in between, so it doesn't matter which order we do it in. Now, on both of these, the next thing we're going to care about is the center point. So for this hyperbola, if we look for the center right here, that is at 2, 3. The x value is 2, so we're going to put minus 2 in with our x. The y value is 3, so we're going to put minus 3 in with our y. And then we need to basically know how wide our hyperbola is and how tall it is. So it is 6 wide. And so that means that underneath x, we're going to put half and squared of 6. So we're going to half 6 and get 3, square 3 and get 9. That goes under x because it's talking about left and right, which is what x is. And then we're going to do the same thing for our up and down. We're going up and down 2. And so when I half 2, I get 1. When I square 1, I get 1. So there's a 1 on bottom. If this was multiple choice, then we would see this without the fraction on y, because if it's over 1, we don't really need it to be over 1. We can just write it like this. But if it was free response, then either answer would be fine. On the ellipse, we're going to do the same thing except that, except that we're going to do the same thing now. Instead of finding the length and height of our box, we're finding it of the actual oval. Our center point is -1, 0. So the x value -1 puts a plus 1 inside with x. The 0, you can put plus 0 or minus 0, it doesn't matter. And in actuality, what that means is that our answer, our best answer, would be to have just y squared instead of having y minus 0 squared. On the bottom of each fraction goes what we're going left and right and up and down, half and squared, just like it did on the hyperbola. So this is 8 wide. And so underneath 8, we're going to put, if I half and square, so 4 and 4 squared is 16. And then on the up and down, which is what goes under y, that's going all the way up to 7, down to 7, so that's 14. We're going to half and square 14 and get 49. I went through that pretty quick because it is something we've already done. So if you need more help with that, you can go and look for our Chapter 9 review, which I realize this is the Chapter 8 review. We actually did Chapter 9 before Chapter 8. That's where conic sections are, and you can get a more detailed review of these two things in that video. On number 3 and 4, we're asked, and this is now the new stuff for this chapter, we're asked if the sequence that we're given is arithmetic, geometric, or neither. If it's arithmetic or geometric, state the pattern. So what we need to remember is that arithmetic sequences, you add to get each term, and geometric sequences, you multiply to get each term. And we would also include the opposites. If we're subtracting to get each term, that's still arithmetic. If we're dividing to get each term, that's still geometric. The neither case would mean that either it's not actually a pattern at all because they're mixing things together, or it could just be that it's just not one of these two things happening. So when we look at number 3, -4 to -20, -20 to -100, and -100 to -500, each of these, to get the next number, we are multiplying by 5. And so that is a geometric sequence whenever I multiply by something. And then to state the pattern, I would just say that you multiply by 5. Then you could assume, I guess if you wanted to, that the next type will be arithmetic, but you do want to check, and since we have to write the pattern anyway, to get from 6 to -194, I'm having to subtract something, and it may be easier to look between -194 and -394. We're subtracting 200 on each of these, which means that this is arithmetic. And so our pattern is subtract 200. And one of the things with this is that if you can tell that it's either geometric or arithmetic, but you can't tell what the pattern is, for a geometric, we divide. We do the second term divided by the first term, and that will give us what we're multiplying by. On the arithmetic sequences, you take the second term and you minus the first term, and that tells you what you're adding, which is a -200. So that's really like you're subtracting 200. So that's how you tell which kind of sequence it is. Now we're going to find the missing terms here. There's a bunch of different ways you can do this, including just guessing and checking. You can try to guess what you would add to each one and see if you get all the way to 47 or if you got too high or too low. You can kind of reason it out by subtracting and then saying, well, how many times am I having to add something? And that will help you find D. But since we have this right here, which is our formula, the other thing we can do is say 47 is the 5th term in this sequence, and 19 is the 1st term in this sequence. And so because I know the 1st term and the 5th term, I can plug into this formula. A of n in this case would be A of 5, which is 47. A of 1 is 19. And since 47 is the 5th term, what we would put in for n is 5. So we're solving for D because we don't know right now what we need to add to get the next number. So we'd subtract 19 and get 28. 5 minus 1 is 4, so this is really 4D. We're going to divide by 4 and get 7 for D, which means that I'm adding 7 to get each number. So the next number here would be 26. I add 7 again and get 33. Add 7 again and get 40. And there are definitely other ways that you could do that where you didn't have to use the formula. But if you couldn't figure it out another way, the formula is a good option. And especially on this next one on number 6, it's really, really easier probably to, well, I don't know if I'd say easier. It may be easier to use the formula than to try to do it however you did number 5. Assuming that you didn't use the formula on number 5. So we're saying that 2 is A1, and that the reason I said that 47 was the 5th term is because I counted how many terms there are. Like there's 1, 2, 3, 4, 5 terms here. So this is A5. So it's going to be similar, except that we're using a different formula because it's a geometric sequence. We're multiplying to get each term instead of adding. So 2,592 has to equal A1, which is 2, times R, which is what we don't know right now. N is 5, because 2,592 is our 5th term. So we're going to solve this. And you may at first kind of be stumped on how to solve this. We want to get R by itself, so we definitely need to divide by 2. Which gives us 1296. And then 5 minus 1, we can go ahead and change into 4. And so if I have r to the 4th equals 1296, I want to 4th root this, because to get rid of a 4th power, you do the opposite, which is to 4th root. And off the top of my head, I don't remember what the 4th root of 1296 is. It is 6. Go figure. So r is 6, which means that we are multiplying by 6 to get each term. So 2 times 6 gives us 12. 12 times 6 gives us 72. And 72 times 6 gives us 432. And it was easy to tell that we got it right, like that we're doing okay on this one, because 40 plus 7 gave us 47. You might check, does 432 times 6 really give us 2592? And it does. So if you worked this out and got an R value and then it didn't finish all the way, that would mean you did something wrong when you were solving. So you'd want to go back and check that to see what you did wrong. On 7, we're going to find the sum of the arithmetic series they described. They give us this formula here. This is only one of the two formulas we had for arithmetic series, but because they gave us A1 and AN, which is here and here, and then they gave us N as well, we'll just be able to fill this in, no problem, and just solve. So we're finding the sum of the first 12 numbers. We know that there are 12 terms, so we do 12 over 2. The first term is 6, and the last term is 116. And if you were to try to do this without the formula, they didn't give us enough information to know what our common difference is, so that'd be super tricky. Some people, I've noticed, just like add all 12 numbers together. Well, we don't know what those 12 numbers are, so we should go ahead and just use this formula. So this is 6 times 6 plus 116, which is 732. So that is our answer for our sum. On number 8, it says to find the term named in the problem. So they said find A of 10. So we're finding the 10th term. They give us the formula in the instructions. And they even tell us what the different letters in there mean, which is nice. One thing that they didn't tell us outright is what the first term and what R is. What R is? What R are? Never mind. Our first term is 3, and then we look at what we're multiplying by to get each term. That's R. So in this case, R is 3. So we're going to fill this in. We want A of 10. It's 3 times 3 to the 10 minus 1. When you type this in, make sure that the exponent is an exponent, like the whole 10 minus 1 should be in the exponent, or you could do 3 times 3 to the 9th. What you can't do is say that this is 9 to the 9th, because that 3 and the 3, that's not the order of operations. You have to do the exponent first, so you do 3 to the 9th and then you times it by 3. Because what's actually happening here is that we have, if we have 3 times 3 to the 9th, we're really doing 3 to the 10th, because your exponents add together when your bases are the same. But you can just type this in exactly how it looks. This is 59,049. So you could say that that escalated quickly if you wanted to. Now, let's talk about summation notation, or it's also known as sigma notation. That's where you have a sigma, which is a Greek letter that in math represents finding the sum of something. The way this works on number 9 is you start with the bottom number and you plug in to the expression they give us. So we're going to do 2 times 1 minus 6. But then we're going to keep going and we're going to put the next number. So we're going to do 2 times 2 minus 6. And then we're going to keep going, and we know to stop when we get to the top number. So 5 will be the last number that we plug in. There's also a way to just type this into your calculator under the math menu if you wanted to go check that out. But this isn't really that bad to just do by hand. If we do each of them separately, we'll get this. These are our 5 different numbers. If we add those together, well, they all cancel each other out. So in this case, our sum is 0. That won't happen a lot of the time, but in this particular case, it happened that we got 0, and so that's the sum. If you just plugged in the numbers and just listed the sequence, you wouldn't be done. You'd have to still add them together because we are being asked because of the sigma that is telling us, hey, add these together. Now, on 10, it wants us to write the sigma notation that represents this. And so when we write sigma notation, we have to write the funny looking E. We can pick whatever letter we want here. So you can either pick M, because that's what they picked on 9. We can pick N or K. Those happen a lot. But we definitely want to put 1 on bottom, because that way we can say, well, this is 1, 2, 3, 4, 5. There are 5 terms, so my top number will be 5. If you try to start with 0, then that wouldn't work. You'd have to do 0, 1, 2, 3, 4, so we'd end at 4. And then that might make finding our expression more complicated. There's a bunch of different ways that we could come up with this rule, but one of the easiest is to say, well, I'm adding 1 to each number. That's the pattern that's going on here. I'm starting at 501 and I'm adding 1 each time. So we're going to have 1 in, because we're basically adding multiples of 1 to each thing. But when I plug in 1, I want to get 501. Right now, if I plug in 1, I get 1. So I need to add something to this to make it to where I get 501. I'm going to have to add 500 in order to get that. So when I plug in 1 now, I get 501. When I plug in 2, I should get 502. When I plug in 3, I get 503. So this is the correct sigma notation for what we want. There may be other ways that you could write it that work, but if you have something else that you think works, make sure that you plug in 1, 2, and 3 at least, if not all the way to 4 and 5, just to make sure that it really does give you these numbers in this sequence. Plugging in and getting just the first term doesn't guarantee that you got the right rule. You need it to get 2 or 3 terms before you know you got it. Now, on this particular problem, 11, it says determine the number of terms in each arithmetic series. Now, there's no formula in these instructions, but if we look back to number 7, there is a formula here for arithmetic series. S of n equals n over 2, parentheses a1 plus an. Now let's look and see if this works. They gave us Sn, which is on the left. They gave us A1 and An, that's these things right here. What they want is n, so we will be able to solve for that. So we just need to plug everything in and solve. So 1050 equals n over 2, and then 5 plus 100 is inside of our parentheses. Now, there's a couple different ways you could go about solving this. We can do what's inside of our parentheses right now and then put it in front, like 5 plus 100 is 105. So this is really 105n over 2. And so to get rid of 105 in front of that n, we would do 2 over 105 on both sides, because that's how that cancels. Like that cancels the top and the bottom. So that ends up giving us 20, if I'm not mistaken, because 1050 divided by 105 is 10, and then you times it by 2. So n is 20. And that's what they wanted us to find, was n. So we're done. There are 20 terms in this series they gave us, where if you do 5 plus, if you start with 5 and end with 100, and the sum is 1050. Okay. 12 and 13. Determine if each infinite geometric series has a sum. Explain why or why not. So what's happening here is we have a ... on the end of each of these that says that this series is going to go on forever. And because we're either adding or dividing on these problems, that means that either our sum is going to go all the way up to infinity, or our sum is going to end up evening out and going towards some number that we can find. And the way we figure out which of those it is whether our numbers are getting bigger or getting smaller. If our numbers are getting smaller, like on number 12, that means that it has a sum. So we'd say that this series has a sum because the numbers are getting smaller. You'll notice I wrote a complete sentence, which, I know it's math class, but you can do it. On this other one, this is actually the same numbers, just in the opposite order. Now, if we think about what our next term would be in our next term, we're just going to get bigger and bigger terms, 64, 128, 256, and so on. And so because they're getting bigger, if we try to add up all these numbers, our sum will just keep getting bigger and bigger, which means that there is not actually an infinite sum for this. So we'd say that this series does not have a sum because the numbers are getting bigger. There's different ways you could write this, obviously, but the gist that you want to have, the reason that it either does or does not exist, is because either our numbers are getting smaller, which means it exists, the numbers are getting bigger, which means it does not exist. You could talk about what r is. If r is less than 1, then it exists, and if r is greater than 1, then it does not exist. So all of it, though, is going to have to do with the same basic concept. Now that we know that, it says on 14 and 15 to evaluate the infinite geometric series that's described, and then it gives us the formula, which this is a pretty easy formula to use. S equals, and since it doesn't say that it may not exist, then we can trust that it exists. And we also know because r's are less than 1. So 250 over 1 minus 1/5 is the first one, and so we do 250 divided by 1 minus 1/5. One of the things with this is you may not get a whole number answer. Like this says 312.5, or depending on how you typed it in, you may have gotten 625 over 2. Either answer is acceptable, so whichever one you got is fine. On 15, r is less than 1 again, so we know this will actually work. What should happen if r is bigger than 1 and you try to use the formula is the answer should actually not make sense. If you think about adding the numbers together, you should get a negative number. Like if we used it on, sorry, let me go back. If we use that formula on this, our r is 2, so we do 4 over 1 minus 2, which gives us negative 4. How in the world can we add 4, 8, 16, 32, and a whole bunch of other numbers together and somehow get negative 4? None of those numbers were negative. Nothing is going to make them negative. So the answer you get from the formula doesn't make sense unless r is less than 1. So we're going to do negative 1 divided by 1 minus 1/4. Which again, you may, depending on how you type it into your calculator or the type of calculator you're using, you may get a decimal, which is negative 1.3 repeating, which as a fraction is negative 4/3. Either answer is okay, so whichever one you want to do is fine with me. So that's 15. Now we're going to start talking about permutations and combinations and then probability. So the biggest issue is that there is a difference between permutations and combinations that may seem kind of subtle or whatever, or may be hard to distinguish between them. And so what we do is we say that when you have permutations, we say that the order matters. And with combinations, we say that order does not matter. And so, to me, the easiest thing to do is to actually have some concrete examples of each one. A permutation would be where we have to elect, or we're talking about how many different ways we can have a president, a vice president, and a secretary. Whereas similarly, a combination would be if we just want to elect people to a 3-member committee. In both cases, we're taking more than 3 people, most likely, and putting them into 3 spots. But for a permutation, it matters which spot you get. Being a president is different than being a secretary. On a combination, it doesn't matter when you got picked. It just matters that you got picked to be on the committee. Another example would be like whenever you do first, second, and third place would be a permutation. If you are trying to arrange things in a line or a row. That would be the case. But combinations is where we're just trying to take a certain number of people and pick them to be something. The calculations for this, there is a formula for it. We're just going to use our calculator for permutations. You go to math and you go over to PRB and you want to pick NPR for permutations, P for permutations. And combinations, we do the same steps, except we're going to pick NCR. So the question on 16 and 17 is going to be which of these, on each of these, are we going to do a permutation or a combination? And the N in our formula is always the bigger number. R is always the smaller number. If they're the same number, then it wouldn't really matter which number you put where because they're the same. Sorry. Okay, so in a class of 20 students, a teacher will randomly pick 4 students to pass back papers, and how many ways can the students be chosen? Well, so the question is, does it matter if you're picked first or if you're picked last to pass out these papers? Or does it just matter that you got picked in general? It may matter to you personally, self-esteem wise, but in actuality, it doesn't matter which of the 4 students you were picked as. It just matters that you were picked because now you have to get up and move around and try to remember everybody's name so that you can pass back the papers. That means that this is a combination. So we're going to do NCR on our calculator. When you do that, you're going to type 20 in first and then go to math and PRB and pick NCR and then type in 4, unless you have a really new calculator, and those will actually like give you spots to fill in, and so that is helpful. If we do 20 NCR4, we get 4,845. And that is a very different number than if you did NPR, because NPR would end up being a much bigger number, because we'd be saying that, oh, well, if you got picked first, that's different than you getting picked last, where in actuality, we just care that we got picked. On 17, it says how many different ways can 8 people line up to get haircuts? Well, in this case, since you're lining up to get a haircut, it would matter to you if you're first or if you're last. It's not the same as to say, okay, well, I'm just in the line in general. There's 8 people. They're going to be in the line. There's 2 different ways you can do this. This is like the lining up the books on a bookshelf that we did, where we said, well, there's 8 places in line since there's 8 people. 1, 2, 3, 4, 5, 6, 7, 8. 8 people can go in the first spot, but then that only leaves 7 for the next spot and 6 for the next one and 5, 4, 3, 2, 1, which is the same thing as saying x 8 factorial, which is also in the PRB menu under math. Or if you just said, okay, the order matters here, this is a permutation, there's 8 people in 8 spots, we could do 8 in PR8, and that would also give us the same thing. Either way, we get 40,320. Incidentally, if instead you had done 8 NCR, 8, you get 1. So if you were trying to say that, oh, the order doesn't matter when we line up, and you picked the wrong thing and did 8C8, you're saying that there's basically only one way for 8 people to line up in 8 ways, because every different way that we put people, we're still putting the same people. So that's another difference between permutations and combinations. So that can be tricky. You just want to try to remember that, to think about, okay, does the order here matter or does it not matter? Let's talk about probability. So we are starting with a jar that has 4 red, 2 blue, and 6 green marbles. That is a total of 12 marbles. And so when we find the probability, the total being 12 is going to give us the bottom number in most cases. We want the probability of choosing a red or a blue marble. So we want to know how many red or blue marbles there are. Since there's 4 red and 2 blue, then together there are 6 red or blue marbles. And we're going to simplify that into a nice fraction of 1/2. This next one, 19, says without replacement, the probability of choosing 2 marbles with both marbles red. Well, if we are not replacing the marbles, that means after I pick the first marble to be red, then I don't have that marble anymore. So the first one being red is 4 out of 12 because there's 4 red marbles and there's 12 total. But to get the second marble and to get it to also be red, since we took out a red marble, there's only 3 left, and since we took out a marble in general, there's only 11 marbles left. We will simplify this and multiply it out, or multiply it and simplify it, whichever order is fine, but we should get 1/11 as our answer. The opposite of that is to say with replacement, and so that means that whatever marble we take out the first time, we're going to put it back in, which means that the two probabilities are not affecting each other. Like we're going to do the probability of choosing a blue marble, which is 2 out of 12. But then we're saying, I'm going to take that, I took out a blue marble, I'm going to put it back in, and now figure out the probability of a red marble. Since we put it back in, that's 4. It would have been 4 no matter what, even if we had not put the marble back in. But the bottom number is still 12, because with replacement means you put the blue marble back in. We're going to multiply this out and simplify, which gives us 1/18, I think. Well, that was not what I meant to type in. Yep, 1/18. So when you're replacing, if you replace it, it means it goes back in, and so both of these should have 12s on bottom. When you're not replacing, then each subsequent one you're doing should have, like if we did 3 or 4 or 5, each time the bottom number would be going down because we would be taking out marbles, so we'd have fewer total marbles. So now we're talking about probability of selecting cards at random from a 52 card deck. What's important for you to know is there's 2 colors in a deck, red and black. There are 4 suits: spades, clubs, diamonds, and diamonds and hearts. And then there are 13 there are 13 types of cards, I guess we could say. We start with ace, and then we have 2 through 10, and then we have jacks, queens, and kings. We're assuming there are no jokers because that would not make there be 52 cards. And so if there's 2 colors, that means, and there's 52 cards, that means there's 26 of each. If there are 4 different suits, then that means there's 13 of each suit. If there's 13 types, then each type of card has 4. So there's 4 jacks, 4 queens, 4 kings. Hopefully you already know that, or that jogged your memory, but if you haven't done much with cards, you may not know how many cards there are. So the probability of selecting a king, there's 4 kings and 52 cards, and so we'd simplify that and get 1/13. A diamond, there's 13 diamonds out of 52, and so we simplify that and get 1/4. This last one, the probability of selecting a black 7 or any 8, well, if there's 4 7s and we have 2 colors, that means there's 2 black 7s. Any 8, there's 4 of them, so together that makes 6. We put that over the total number of cards, which is 52, and then simplify. And so that's going to give us 3/26, which is our answer.